All right, GCSE chemistry crew. You know those required practicals can make or break your exam, right? Well, today we're diving deep into a big one. Required Practical 5, all about the rate of reaction. Let's get you prepped to absolutely smash it. So let's start with the big question, the one this whole practical is trying to answer. How on earth do we measure how fast a chemical reaction is going? I mean, you can see if something's fizzing like crazy or just kind of bubbling along, but how do we put a real number on that? That's what we need to figure out. And to do that, to answer it like a proper scientist, we've got to be super clear on our terms. So, first things first, what is a rate of reaction? Okay, so here's the deal. It's basically just a fancy way of saying how much stuff changes over a certain amount of time. Think of it like this. It's a measure of how quickly your starting chemicals, the reactants, get used up, or how fast the new stuff you're making, the products, appears. And hey, there's a super simple formula for this. The mean rate is just the quantity, how much stuff, divided by the time it took. Easy, right? So if you're collecting a gas, your units will probably be something like cubic centimeters per second. Or if you're weighing how much something's mass changes, it'll be grams per second. Makes sense. All right, let's get into the nitty-gritty, the actual experiment. For AQA, this required practical is all about investigating how one specific thing, concentration, messes with the speed of a reaction. So, what's our mission here? It's simple, really. We want to find out what happens to the reaction speed when we fiddle with the concentration. We've got a hunch, right? We're basically testing the idea, does making a solution stronger make the reaction go faster? Let's find out. Now, the cool thing is, AQA gives you a couple of ways to tackle this. Method 1 is all about measuring gas. And method 2, that one's about watching a solution get cloudy. It's a bit like a magic trick. We're going to look at both. Okay. Method 1, measuring the gas. So picture this. You take some hydrochloric acid, you drop in a strip of magnesium, and boom, hit that stopwatch. As it fizzes away, it produces hydrogen gas, which you collect in a gas syringe. And you just sit there and every, say, 10 seconds, you write down how much gas you've got. You keep doing that until it stops bubbling. And then the important bit, you do the whole thing all over again, but this time with a different strength of acid. Now from method 2, the famous disappearing cross trick. This one's pretty cool. You mix two clear liquids, sodium thiosulfate and hydrochloric acid. When they mix, they start to form this cloudy yellow solid, a precipitate of sulfur. So what you do is you draw a big X on a piece of paper, pop your flask on top, mix the chemicals, and start the timer. Your job? Stare at that cross and hit stop the instant you can't see it anymore because the solution has gotten too cloudy. So simple, but it works brilliantly. Okay, listen up because this is where the big exam marks are. It's all about your variables. To make this a fair test, and you have to make it a fair test, you're only allowed to change one thing on purpose. In our case, that's the concentration. That's your independent variable. Then the thing you measure to see the effect is your dependent variable, so the time it takes. And everything else, absolutely everything else, has to stay exactly the same. We're talking temperature, the total volume of the liquid, all of it. Those are your super important control variables. Right, so we know how to do the experiment. But just getting results isn't enough for a top grade, is it? We need to explain why it happens. And the key to unlocking that why is a massive idea in chemistry called collision theory. Collision theory is actually pretty logical when you think about it. It says, for a reaction to even have a chance of happening, two things have to be true. One, the particles have to actually bump into each other, collide. Makes sense. 2, it can't just be a gentle tap. They have to smash into each other with enough energy to actually do something, like break old bonds. And that minimum whack of energy they need, that's called the activation energy. Okay, let's connect this fact to our experiment. Imagine a big, empty room with only a few people wandering around. That's like a low concentration. Are they going to bump into each other very often? Nah, probably not. There are fewer particles in the same amount of space, so you get fewer collisions happening each second, which means a slower reaction. Simple as that. Now, what about a high concentration? Well, imagine that same room, but now it's packed wall to wall with people for a concert. It's crowded. People are going to be bumping into each other constantly, right? That's exactly what happens here. You've crammed way more particles into the same space, so they collide much, much more often. And more collisions per second means, you guessed it, a faster reaction rate. See? It really is that simple. Okay, experiment's done. You've got a page full of numbers. Now what? Well, now comes the fun part. the part where you turn that raw data into a real scientific conclusion. If you did the gas syringe method, it's graph time. Remember, time always goes along the bottom on the x-axis, and the amount of gas you collected goes up the side on the y-axis. What you'll see is a curve that starts off really steep. That's when the reaction is going full steam ahead. Then it'll start to level off, getting less and less steep until it goes completely flat. That's when the reaction is over. And here is the absolute golden rule for reading these graphs. You have to remember this. The steepness of the line, the gradient, is the rate of reaction. So, super steep line, super fast reaction. A line that's getting a bit lazy and shallow, the reaction is slowing down. And a perfectly flat line, game over. The reaction has stopped. Okay, ready to level up? This is a higher tier skill, so listen closely. What if you want to find the rate at one specific moment in time, not the average? Well, you pick a point on your curve, then you take a ruler and carefully draw a straight line that just kisses the curve at that one point. That line is called a tangent. All you have to do then is work out the gradient of your tangent. Remember, change in y divided by change in x. And whatever that number is, that's your reaction rate at that exact instant. Pretty neat, huh? Right, let's bring it all home. We've done the practical, you've understood the theory, now let's talk exams. What are the examiners actually going to ask you about this? Okay, here's what the examiners are looking for. It's like a checklist. Can you describe the method clearly? Yep. Can you pick out the independent, dependent, and control variables? For sure. Can you use collision theory to explain why your results are what they are? Absolutely crucial. And of course, can you plot a good graph and read it properly? And for those top grades, can you draw a tangent and calculate the rate? Tick all those boxes and you're golden. Let's look at a classic exam question you might get. Something like this. Now, pay attention to the words they use, like explain and using collision theory. These aren't suggestions, they're direct orders. The examiner is telling you exactly what they want to see in your answer. So what does that perfect answer look like? It's a recipe. First, you say that higher concentration means more particles are packed into the same volume. That leads to collisions happening more frequently. Now, for the 5-star, top mark answer, you need to add one more little detail. It leads to more frequent successful collisions per second. That means collisions where the particles have enough energy, that activation energy we talked about. Okay, so you've absolutely nailed how concentration affects reaction rate. You're an expert. So to wrap up, here's a little challenge for you. Now that you know all about collision theory, how would you use it to predict and explain what happens when you increase the temperature instead? I'll give you a hint. It's not just about how often they collide, but also how hard they collide. Think about that. That's your next level of understanding. Thanks for tuning in.